Good afternoon, everyone, and thank you for joining us. My name is Ditte, and I'm happy to welcome you all to today's session on Experimental Modal Analysis with ARTeMIS Modal. Pelle Andersen will be starting the presentation shortly, and we expect the session to last around an hour or so. As always, you are very welcome to ask questions both during the presentation and also afterwards. Just to let you know, we have disabled the chat function to avoid any interruptions, so please use this Q&A function at the top left corner if you want to ask any questions either during or after, and Pat will make sure to answer all questions after the presentation. Please also be aware that we have disabled the cameras and the microphones, and we would like it to stay that way, also to avoid any interruptions during the session. With that, I think Pelle is ready, so I will hand it over to him. Thank you, and enjoy the session.
Yeah, thank you very much, Ditte. And I always like to say welcome to this webinar here on experimental modal analysis. That, as Ditte said, I think we expect something like 1 hour or so. Today I will try to go through 3 things at least, probably more, but at least I'll try to give a little introduction to experimental modal analysis, and then make a demonstration on a structure that I have here in my office, and then also touch some of the news that we have in our latest version we just released, that is version 8.1. So this is what we are going to go through now, and as an introduction, let me just show this one here that I have probably shown to some of you many times, but it's a nice little illustration of what it is that we are working with here. You should imagine that we have some kind of structure that is vibrating due to some kind of vibration. In this case here, some kind of, you say, forced vibration that we can measure. And then we are also measuring different places on it, how it's vibrating. So the response of this structure here. And based on this information here, modal analysis can actually take us from this physical domain that you could imagine we are in on this side here, to what we call the modal domain on the other side here. Here things are much more structured than it is when we look at the vibrations in the physical domain. Here we have things split into the different modes of vibration, and that means that we have the first, you say, mode shape of the first mode looking something like this. Along with this one here, there is a natural frequency of this mode here, and there is also a damping ratio. These are 3 parameters, where one of them is a vector, are the ones that describes a dynamic mode. Let me just make this visible. So we have a set of these for each dynamic modes, and there will be many of these on a structure. And how many we have depends, of course, of the structure, but also how we can excite and measure it. We can do this analysis in different ways. We can use it, this experimental modal analysis we're talking about today, but also another thing that is called operational modal analysis that I will talk about next webinar I will be giving. And no matter which one it is, the idea is that we want to use some tool that can extract modal parameters from measurements of the structure. So this is the idea of what we are doing here with our software, and also the idea of this webinar here. When it comes to experimental modal analysis, as I said, we have to assume we have a structure that we want to find the modal parameters of. This structural system here, we have to assume that it's a linear structure, which means that it doesn't really matter how you say excessive we are exciting this structure here. No matter what level of excitation we are providing, we should be able to extract the same modal parameters of it. So this is one of the 2 things that is very important. The other one is that during the test here, we have to assume that this structure here is time invariant. We cannot have that the structure is changing its properties, at least during the test, because then whatever we are getting out will be some kind of mean values of what has been going on during the time. So we have to assume that the modal parameters, they are constant values that we are extracting from the structure. And this is what time invariant behavior means. So we have these two things that you have to assume about the structure. And then in experimental modal analysis, we are supplying some excitation that we can measure. And we have to be able to measure all the excitation that we are supplying. At the same time, we are also measuring how the structure is responding to this excitation. And we do that with different types of sensors, typically accelerometers. So we have, you say, measurements of both input and output, excitation and response, and whatever we call it. All this we have available on both sides, and this is what we need when we do experimental modal analysis. And what we get out from that is the ability to construct a function we call a frequency response function. That is the, you could say, transfer function that describes the actual structure's behavior. We call it in short an FRF. And all things that we do in ARTeMIS Modal that relates to experimental modal analysis is based on that we have these FRFs available. So we need to in some way get them. And this is what we are trying to do and in the software, and I will try to explain how we can do in general in the software. So just to describe it very briefly what it is that can be done, you can assume that we have some kind of structure here we would like to test. What we will do is we will try to put one or more sensors that can measure the response of the structure. And then we will excite the structure in some points and measure this excitation. So here it's an impact hammer that we are using, and this impact hammer here has a force transducer here in the tip that allows us to measure what's going on when we impact the structure. We can then measure the impact as this sequence you can see down here. At the same time, the structure will respond, and here we will then see how this looks like. It will be a kind of a free decay. The structure will vibrate for a while, and then this vibration will die out. These two things here are measured in time domain, and they are then put or brought to a frequency domain by something we call fast Fourier transformation. And we get a spectrum of the response, and we get another spectrum of the force or input. And these two can be divided with one another in different ways to produce what we call the frequency response function. That is this nice function that only describes whatever is going on inside the structure. And this is the basis of what we are doing when we do fitting in different ways to extract the mode parameters. There are two different ways in general that one can do when it comes to experimental mode analysis. You can either use an impact hammer and then do some kind of impacting different places on the structure where you would like to know the mode shape. Or you can also do the opposite. You can try to mount some kind of device, a shaker in this case here, that will then shake the structure in one or more fixed positions. And then you will measure the output in different locations. That can either be that you mount all your accelerometers, the places you would like to have it, the measurements done, or you move around with your accelerometers. In either way, we get the information that is required in order to be able to estimate the frequency response functions, and then proceed from there with doing the extraction of the modes from these. ARTeMIS Modal is, you could say by birth, a platform that was designed for operational mode analysis. And then we, after some years, we extended it so that it also can deal with experimental mode analysis. And to do that, you actually have to either have an additional module we call it a plugin for ARTeMIS Modal that can then open up for that we can do this experimental modal analysis. You can also have a special version that we have designed that is called ARTeMIS Modal EMA, where we have completely removed everything that is not related to experimental modal analysis in the software, and you have a version that is completely designed to do this type of analysis. But otherwise, if you have ARTeMIS Modal, you just need this experimental modal analysis module. And if you also want to do impact testing with the software, you need an additional module that can allow you to communicate with hardware, data acquisition hardware. And this is one thing that I would like to show a little bit later here. So these are the different, you could say, modules that are required in order to do experimental modal analysis. FRFs can be obtained in different ways. If you have measurement files available from some external measurement system, you can imagine you have measurement files that contains both the force measurement and also response measurements. You can actually import these time series files directly into the software and then use ARTeMIS to process the time series files to produce the FRFs. This is one way of doing it. Another one is to upload the FRFs already produced by external software and then use those to do modal parameter fitting in ARTeMIS. Typically here we are using files of the universal file format type. I will try to show that in a second, but otherwise there are other formats available also that can do the same. And finally, there is the possibility to do an impact testing directly with the software. So here you just prepare everything inside the software and then you use the equipment that you have in order to produce the FRFs directly by using ARTeMIS. So we have these three options here available. In order to, you could say, try to upload from universal file format, let me try to show you here the software first of all. This is ARTeMIS Modal that we have running here. And when you open it up, you see this kind of little dialog here that allows you to then produce different types of projects depending on what licenses are available. I normally go to this create new project and then I right click here and then I have this little list here of different types of projects I can create. And you can imagine that in this case here we would like to create an EMA project using universal file format. And to do that, then I click this one here and then I get this dialog here where I have to select at least two files. The first file I need to find is one that contains the geometry of this particular structure I'm testing. And then another set of files that consist of the frequency response functions. So we can try to see, if you click here, we can find the file. You can see I have here a folder where I have a test of some kind of automotive structure. And if I load the first one here, this is actually where I have my geometry in. I can try perhaps just to open this one here and then see if I get some kind of, let's see if I can get this over here with a little, oh, now it wants to update. I don't want to update file. So this is this type of file here. So here we have a universal file format file where we have definition of the nodes, the geometrical nodes of the structure. Here is a section where we have definition of the trace lines between them, and this is a definition of the triangular surfaces that are connecting them to make this structure look solid. So it's a quite simple format for the structure here, but we can try to open this one here. And then the next we have to open is a file, one or more files that contains the FRFs of this particular test here. And here we have 4 different ones here. and they have similar kind of structured information in universal file format, but now it's actually the FRFs that are stored in these files here. So you can load one or you can load many files in here. Ultimately, we should have all the different entries, you could say that all the different places we have impacted loaded through one or more files. So we can try to open this one here and then click finish. And now we get a new one here, a new dialog. And this is one that we have had for some time now, where you can now select if there are different types of information in the file. It may not only be FRF, for example, that is in these files here. Maybe there's other things that you don't really need in this project here. That means you can actually disable it. You can deselect it here. And otherwise, this also gives you an overview of what each of these FRFs actually have of definitions here. We can see that there is an acceleration response and the unit here, and we can also see that the force is in Newton and so on, and we can also see the directions. All of this looks good, but you could imagine actually that some of this was not good. Maybe there was something here missing or something. Then now in this version 8.1 of the software, this is not just a readout we have. Now you can actually go and you can change. You can simply click here and then you can change if some of this needs to be modified to something else that we support in the software. So this way here, all the places where you can see you have this bold black text here, this is actually places where you can edit the information that is here in order to make it better suitable for the analysis. There is also a traffic light over here. This is either red or green. If it's red, we have already in the upload determined that there is something in this particular frequency response function, for example, here that is not working. It could be that you did not put a proper direction, for example, in it. Then this one will turn red here. And this is then where you have then to go here and then do some kind of editing if you want to have this one here also included in this project here. So now this dialog here actually give us some more flexibility to use data that may not be completely up to date or workable initially, but we can now make it work so we can extract some modes. Here everything is green, as we can see, so we will click import all. And then after that, a project will be created with this data here. Here we have the mode indicator function that is just a way to show all the FRF information in a single diagram. I will not go further with this project here, but this is just to show you how you can get it from universal file format and how you can actually also use this, dialog we have here that I think we also have presented here. So here I just have the same information that I just showed before, that we have this new more active import preview dialog here available. Otherwise, what we can do is we can try to create a project with the software, and we can also try, or I can try to then do an impact testing. In order to be able to do that, I will need to first create a geometry, and then I need to do something that allows me to create the FRFs that we will be using for the analysis. Here we will need to have a kind of a communication established with some data acquisition hardware. We call it a DAC plugin. So you need some kind of, you could say, module in ARTeMIS that can actually communicate with some of the hardware that you may have. We support different types of hardware. I'm showing a couple of examples here. So we have the National Instrument. Here is very versatile because it's a range of different modules that is actually supported in this way. There is also HBM here, for example, that has these quantum X units of different channel counts that we support. And otherwise, there are a list here of others that is available. In this case here, in my table here now, I actually have this data acquisition from National Instruments running here, so we can try use that. And the model that we are going to test now is this, the G-beam structure. I think some of you may have seen it before. It's a nice structure that has some well-separated modes, but it's a little bit more fun than just looking at a plate. It has some two-dimensional modes in this case here. And here we have then this configuration of the hardware that we are going to use. We are going to fix outputs. That means we are going to fix some accelerometers in some position here. And then we will be rolling the input. That means we will take this hammer here and we will then be moving around on the structure here. This is one of the options that is available. There are different other options. This is the default one we are going to use. Another one is that we actually fix the inputs and then we are moving around with the outputs. That could be that you have an accelerometer and then you are hitting the same point all the time and then you are moving the accelerometer. And then finally you can also move around with both input and outputs if needed. The reason why we need to know this, you could say there is a kind of an option here under the measurement task in the software. Here we need to know this, and that's because we have this we call a data organizer. This is a tree structure that show you the different channels of the different setups. That means where the different sensors are located on the structure. And in order to know how this one here should work, how it should update and tell it if something is wrong, we need to know which of these configurations that you will be using. So this is simply because of this data organizer here that we need to select this. Another thing that we have introduced here in the version 8.1 is that we now have two different ways basically we can do the estimation of the mode shapes. Since ARTeMIS was born as an operational modal analysis tool, the way it works is that mode shapes, they are estimated in the point and the directions of the response measurements when it comes to operational modal analysis. And then what we did in the beginning when we did implement this EMA module here was, when you now start impacting in different locations, we will use the direction and the location of the impact hammer as our, you could say, basis for making the mode shape. This works nice if you're covering all the points in all the different directions where you like to know the mode shape. But there is another way of doing it, that is to use the directions of the accelerometer or the response signals, and then you make use of those directions and measurements in the impact points. And here we are using the fact that you can measure response in one point and you can impact in another point. This relation between response and impact here is exactly the same as if I impact at this point and measure the response up here. So this is really nice because that means we can actually interchange the things so that we can make use of the response measurements in the impact points. And this is what we are going to do, and this is the default, you would say, setting we now use in the impact testing module. So I think we should try see how this looks here. What I will do is, I will first of all go to the software again. And I think I will try to see if I can change my camera here now. I need to find out where that camera is located. I should have a camera now pointing on the structure here itself. As you can see here now, I hope you can see it. So this is the structure we are going to work with. In the software, I will need to start defining something. So I will just close this project we just made here. And then we will make a new one. So I go here to the button here, this our application button, and then I choose new here. And then this shortcut menu here to the different project configurations is actually also available here. So in this case here, I'm going to use a blank project. I will start all over again. So when I have made this blank project, it's blank, as you can see. And what we are in now, we are in a task we call manage measurements here. You will find this task if you click here on setup, then you can see that manage measurements here. This is where we are actually now located. But this is, you say, the default task we always start up in, because if you have some raw data that you want to check before you start doing any kind of analysis, it makes sense to go here. But in this case here, we don't have anything. We are going to make an impact testing. So the first thing I like to do now is actually to go to the prepare geometry task. And then I want to produce a geometry. And I can do that in different ways, but I'm a little bit lazy this time of day. So I will go here to a folder, and then in the universal file format, I actually have it already defined. So that was a quick way of getting this geometry here created. But otherwise, this can be done inside the software. This has been produced by this task here in an earlier project. But this is the geometry that we are going to test. We will try to put some impacts on these points that you see up here. The lower part here we'll just leave out. That one is standing on this foam that you may see here in the video that is running also. So this is how it looks. The next thing we have to do, that is to define where are we going to measure this one here. So now I go to this task here I call assign DOF information here. And in this one here, I get a larger version of the geometry, as you can see here. And this allows me now to graphically define where the different response and impact positions should be. Maybe you can see on the camera that there is 2 sensors located in the corner, 2 accelerometers. So this will be our, you could say, place of response measurements. I can try now to go here to insert object and define one. I'm going to define one setup here. I was just told that someone wants to see me instead of the test structure, so I'll just shift to me. What we have here now is we have the first setup defined here. I have 2 channels with response measurements, and then I have 1 channel that I'm going to use for the impact test, or the force that is going to be measured from the impact hammer. So the first thing I'll do is I will take the first channel here and drag out. This is my first accelerometer. This one here is pointing in the minus X direction. So I will place it here. I will click this minus X to get it this direction here. Then I'll grab the next channel here and I'll drag it out to the same location here. But now this one here is pointing in the minus Y direction, like this. So this is the 2 accelerometers that are located in this position here. Now we have the third one here. I will start dragging it over here on this position here. This is now going to be the, you say, the force measurement. So in order to make this one a force measurement, I will have to actually create another type of object here. You can see the signal type is right now output. This has to be changed to input. You can also see there's a little icon here that changed from out to in. So that just to mark that it's now an input sensor. We need to change the direction of this one here, because I like to try to use a 45-degree skew direction so that I can both estimate or excite the modes that are going this way here, but also the ones going this way, without having to impact 2 times. So I go here, there's a little other new option here we have here, where you can go here and you can click on the 45 degrees. And now I need to see if I want to have this one here impacting in plus Y and yeah, let's see, isn't it? Yes, it's plus Y and plus X and plus Y, as you can see here. So now this one is impacting this direction here. We can now try to repeat this setup here a couple of times because we have 7 other positions we need to define. So I will choose this replicate option here. I will then replicate this setup here 7 times. And then you can see now the whole list of different setups are inserted here. I need to do something in each of these. I simply need to drag the force of the impact location to wherever I want to use it. You can see now this is just the one below here I'm going to use for this one, and then the next one I can drag over here, and now it has this direction here, but maybe it will be easier I go this way here. So if I now go here to 45 degrees again, and then I use, is it minus X then? Let's see here. No, not that one, no. So we try again. So we have minus X, and then we have plus Y. Yes, this one here. So now it's in the correct direction here, and we can now repeat it one more time. It remembers the last direction when next time you then drag one of these out. So you can see now how we are now at having this part of the structure covered in this way. We can now move it to the other side here, and we can try to do similar things here. So now we will drag it over here to this location here, and now I need to again try to see if I can find the right direction here. So now it's minus Y, I guess, and minus this one here, yes, like this. And then we go here, do the same, and then we are missing 2 more. Go to this location here, and now I need to change again the direction. It's probably the X that is wrong here, so now I guess it's this one here, yes. And now we will take the last one. So in this way here we have now defined that we are going to make these these 8 positions here, and then hopefully we will get something out of that. Let me just save this project here, so we have a little backup here. Good, now we go to the data acquisition part. National Instruments is what we have connected right now. Now we have this list here where you can see it's already figuring out that some of the accelerometers here, they are TET sensors, so we can already now know what kind of sensor it is and calibration and so on. That's good. But what I need to tell is that the impact hammer, that's a force transducer. It has no TET information, this electronic calibration information. So I need to use a definition I have from inside an XML file that is stored on this computer here. Here I have defined it for this impact hammer here. So now I can select this one here in this way. And then I click OK. And now this will be remembered also when I come back again to this project here. It will remember that this was the kind of configuration I was using. So now we're inside the impact testing module. This is where we need to have this data acquisition license in the computer in order to run this. The first thing I have to do is I have to tell that the sensors, the way that I have defined the channels inside the project, is matching the way that I have put the sensors in the data acquisition system. This is the easiest if you do like that. So that means that on the hardware side, the first channel is actually the first accelerometer that I'm using in my project. And the second one is the second accelerometer, and the third is the force channel. If you use exactly the same configuration both places, you can then use something we call auto-assign, where we simply tell that we are using the same channel configuration in the project as we are on the hardware side. And this makes life much easier when we can do that. Otherwise, we will have to do it a little manually by selecting it from this drop-down list here. And now, once we have connected, we can also enable some more diagrams here that allows us to see what's going on. The next we have to do is we have to make a setup of the impact hammer. We do not know up front what level we should use in order to trigger a measurement to be done. Here we need to try to make some impacts on the structure, and then we figure out what is the threshold or trigger level that we need to set. So the easiest way is just to start by selecting what frequency range we would like to measure in. We can just use this sampling frequency that is suggested here, that is the lowest this module is providing. And then we can try to perhaps measure a bit longer like this. Now we can try to start it, and now I will switch my camera back to the structure here. And then I'll try to grab this hammer here, and then try to make some impacts here on, I'll just move this a little bit away. So we will try to, it's going to be a little interesting because I'm going to actually impact on the edge of these, this structure here, which is not the most convenient thing to do. It will be much easier to do it on the surface of it, but we'll do like this. So now you can see we have some impacts made here, and we can stop it and then see what we are getting of suggestion here. That was not enough. I think we will lift it up a little bit more to perhaps something like, let's see, if you come up here, then we probably have something, we can go a little bit further, something like this. So now we have a trigger level in Newton set here, and we also have a pre-trigger time, which is something we need in order to be able to process, you would say, these impacts in a nice manner. If we have a pre-trigger time before the impact, we can use that to actually make a kind of a zero mean correction of this force measurement, which is a good thing to do. So this looks okay now. And then we can go to the next, that is to try to set up the windows that should be used on the force and the response side. On the force side, we normally will choose to have a force window. This window here simply makes sure that after the impact has been made, everything after that is zeroed out, so we just get zeros. That produces a much better spectrum than if we're just measuring a lot of noise in the rest of this signal here. Then the next is, the next we want to do is to just see how does it look. So we would like to use this where we see a raw and the windowed data. That's nice because then we can see how this window is actually looking. So we do that on the force side. Let's wait with the response side. Let me just try to start here so we can see what happens now. So now I'll just impact here again. And then see. I think I need to actually hang on before I continue. I will just stop sharing and then start again because I need to do something in order for, I think, you to hear what's going on here. Hang on. Hang on, I just need speed on here. Try again. Yes. Okay, so I hope that we will try again and see if we can hear something here now. Didn't seem to be the case, but yeah, I hope that there is some sound on your end because I cannot hear anything here, unfortunately. Anyway, this is what it looks like. This impact that we have measured the force here. So we have the impact here, and then you can see how the window is working here. So it goes to 0 here, and then it will zero out everything here. On output, then we have a nice flat spectrum here and most of the frequency range, and this is where all the modes are, as we can see here, so that's pretty good. On the response part here, we have the response here of one of the sensors looking like this. If we are not satisfied with that it dies out to 0 here, we can always add a window here. This is an exponential window that we will then be adding. We have to inform what the level in the end should end up being compared to in percentage to the initial one. And in this case, we can use something like 5%, and we can try to see again how it looks. We get something. Oh, wait, hang on. We probably need to show also the window here. Here we can see how the window is operating and damping out all the response to the end here, like this. So this is possible to do. I think it looks okay, and I think we will stop here and then click OK here for this settings here. And then we can actually get started here now. So what I'll do is I will start, and then now it is indicating over here where my first impact should be. I have another window here I'd like to also show here. This actually helps me following where I am. This is actually a visualization, you could say, of the FRF matrix with the different entries. When they turn green, we have all the impacts that we are needing for this particular location here. So I'll try to see if I can do this this impacting here on this location here. Let's see. Probably not easy. I don't have to. So now it's measuring. I need to get into training here. So we'll just carry on. That was a double hit. And we are finished then with this location here. And we can now proceed to the next. That was a double hit. Oh, that was also, I think. Yes. Okay, and then we have the next. That is over here then. Double hit. So, with luck. Next one. Okay. So now I have to go over here and then do from here. Just turn this around to not confuse myself too much, like this. Yeah. Yeah. Yeah, couldn't find this one. Yeah, that is probably done. We have now everything we need. So let's just save this project here. And then we have done the impact testing with the tool here, with the National Instrument hardware in this case here. And what we can now try to do is just to look at what it is that we actually have of methods available inside in order to estimate the modes. And there are two different types available here. There is a peak picking tool here, where we are using the mode indicator function. That means we are taking the frequency response matrix and we are applying a singular value decomposition to it, which are then allowing us to see everything in a single diagram here and then do peak picking on it. The other one is this rational fraction polynomial, where we are fitting a series of rational polynomials to the FRFs, and then creating a so-called stabilization diagram that allows us now to actually extract the modes. These are the two ways we have. So we can try and go back to the software if I can get it found here like this, and then we can try to go here to prepare data. And here we see now this is the mode indicator function that you see here now showing up here. We can also try to go to the estimation tab where we can actually extract the modes from. And here we can do a peak picking by clicking this new modes button and then pick them out. Or we can try to lower this level here, and then everything that is above the level that I have here, it will now try to fit automatically. So we can try this and see how this looks. We already have here one of the modes, as we can see here, and here we have another one, and here we can really see how it works, that we have impacted in this 45 direction, because it allows us to actually estimate the rotation of this structure here in the two directions then. So this is how it's working, this peak picking tool. Automatic or not, sometimes there are peaks that are not found, so we can see we actually have one here that it's missing, but I can just grab it simply by adding it manually by clicking this button here. Then I can go here and I can double click on it, and now I also get this mode estimated here. The other type of tool we have is this rational fraction polynomial. And here we have to go to a level called a setup level. The top level is not so much in use for this particular. This is more a remnant from our operational modal analysis tools. But if you select a setup here, like I did here, then you can actually now get this kind of stabilization diagram that is right now empty. But up here, we have the model order of the rational polynomial. So that's basically the polynomial order of the denominator polynomial that we have in this rational polynomial. This one is actually equal, the number of parameters there is equal to the number of eigenvalues that we can estimate. So here we can estimate up to 50 eigenvalues. That means basically 25 modes. What I can do is I can just try to click Estimate Models here. And now you can see that all the models are estimated, and from these rational polynomials we are extracting the eigenvalues that give us the natural frequency, that is the red dots that we see here, in this case here. We're also getting, of course, the damping ratio, and from the residues of this particular model, we can also extract the mode shapes. So all that is done through this process that happened when I click this estimate model here. And we get a list over here of the different modes that has been estimated. One thing you might see is that there is in fact something that seems to be a little repeated here. If I zoom in here, you can probably see that this mode here seems to be repeated a little bit, even though there doesn't seem to be any. So if we take a look at these two mode shapes here, animate this one here, you can see they are the same. So this indicates to me that we are having a little bit too high a model order selected. There are simply not so many modes in this FRF here as we are asking for. So a good thing is then to reduce the maximum model order here to something less than the default. So we can try 30 perhaps in this case here. That will give us up to 15 modes. And then I just press Estimate Model again, Models. And now you can see that there is nothing repeated here, and we have all the different modes nicely estimated in this case here. So this is how this tool is working. There is a little bit of clicking, not much, but at least a little bit, which is of course also nice. This is the two methods we have available, and once you have estimated the modes with the different tools, a good approach is then to try to compare it and validate if everything looks the same. The way we do that in ARTeMIS is we will then, in this list here, we have the two different sets of modes. And you can simply click the first one here, and then you can keep your control button down and then select one from down the lower list here. And then you can try to animate them together like we do here. And then you can see if everything looks the same. You can actually operate what you want to animate up here simply by clicking. When you select something here, like this one here, then it's actually the two modes that you see over here that being animated, and they are automatically selected in this list here. So this is some of the features that are available. We have some new features also now in this version here. We can try go back here just to see how this looks. If I just go a little bit quickly here to this one, we have this we call a favorite mode option now. And the reason why we have that is that we like actually to sometimes to keep some modes from a previous analysis when we now start doing the modifications in the analysis. And this can be done simply by right-clicking on a mode that you want to keep. Then you can add it to a favorite section that is kept in this list here, no matter what you do of changes in the analysis. So I can try to do that here now. I can say, okay, let me try to save this one here. I add it to favorites. And I can also take this one here, perhaps. I say these two here I like to keep. And now I like to do some changes here. I can zoom in on the lower modes, for example, here. Let me take this one here also. So now it's only going to be those modes here that is going to be estimated. You can see up here there is nothing now. But that means that we have a new set of modes here from the new analysis, but we still have the other modes here from the previous analysis kept in this way here. So you can repeat this over and over again in order to keep whatever you want to do. And this is available for all estimators in ARTeMIS. Not only for EMA, but also for operational modal analysis. So this is a new feature we just added that we have been asked to do by some of our users. And I think it's a pretty nice little addition. So this is, you would say, what I like to end up with talking. I talked about, I just introduced a few of the new features we have in this latest version 8.1. And I also touched how we can actually get the FRFs either by loading them from files or internally estimate them with impact testing. And here I then also showed one of the new features where we are using this where we're using the output sensors. We put them actually in the impact locations. This allows us now to use the skew directions of the impact hammer to more easily produce, you could say, the information that is needed to excite modes in 2 directions with a single impact. I also discussed a little bit about what hardware we have available, and you saw how National Instruments are working together with ARTeMIS Modal. This is for EMA, but it also works, of course, for OMA measurements. And then I showed you the CMIF and the RFP-Z method briefly, and how to validate modes with them. And of course, finally also how we now have this add favorite modes available. So this is what I wanted to just talk about today. And if you need more information, we have, as usual, our videos at the YouTube. This one, this webinar here will also be located there. And of course, we also have our website where you can download information and the software. And the next webinar will be in June 25, where we are going to talk about operational modal analysis and what news we have there in 8.1. And finally, the next event where you can meet us, that is in Leuven in Belgium, at ESMA conference that takes place in September this year here, over 3 days. There is a modal analysis conference, very well visited normally, so I hope to see some of you there. Thank you very much.